The electric field is a conservative vector field, and we'll investigate this and demonstrate this in the following way. That will evaluate the line integral of the electric field due to one point charge q. So here is the point charge, and well, the physics is not influenced at all by where I put the coordinate system, so I choose for simplicity to put the coordinate system origin exactly where this point charge is located. And then I get this expression for the electric field, which is simple to express in terms of spherical coordinates. So what we want to do now is to evaluate this line integral, and that line integral goes along this curve. I call that curve L. And the curve has a direction, and it takes us from the starting point A along the curve to the end point B. So in order to evaluate this line integral, we insert the electric field here, and then we need to have the scalar product with dl. And now, since the electric field is expressed in spherical coordinates, dl also needs to be expressed in spherical coordinates. So this is the expression for the vectorial line integration element in spherical coordinates with the three spherical components r hat, theta hat, and phi hat. So as we evaluate this scalar product, we realize that actually it's only this first term in dl that will contribute. So as we take r hat dot r hat, that becomes 1, but r hat is perpendicular to theta hat and phi hat, which makes these scalar products 0. So these expressions will not contribute. Expressed differently, you see that when this curve is sort of moving a little bit in the radial direction, the r is non-zero. So in the radial direction, there will be a contribution to this line integral. As soon as this curve moves in the radial direction, there will be a non-zero contribution to this line integral. But no matter what movements this curve makes in the theta direction and phi direction, those will not contribute. And that's because of this scalar product evaluating to 0. Now if we write down this result over here in detail, we will have r hat dot r hat is equal to 1, which leaves dr together with the magnitude of the electric field here. And as we discussed before, these two parts vanish. So to give an example here, if we move in the radial direction, obviously there will be a contribution to this integral. And in particular, we're interested in the radial coordinate for the start point and the end point. So here we have the radial coordinate r sub a, and if we move L here a little bit, this is the radial coordinate for the end point B. So as long as these two are at different places, so to speak, that we've moved effectively in the radial direction as we move along that curve, this will give a non-zero integral. We can realize that. But if this curve would say would stay on a spherical surface here, well, then on the spherical surface r doesn't change, only theta and phi changes. And then on that, for a curve that stays on a spherical surface with its center coinciding with a point charge, then there is no variation in the radial coordinates, so the r becomes 0. The theta and the phi are non-zero moving on that spherical surface, but it doesn't matter as a contribution to this line integral. Okay, so this is a simple 1D line integral, and we evaluate that now using normal integration from calculus in one variable. So q over 4 pi epsilon naught we can consider as a constant, so we need to integrate 1 over r squared, and that primitive function is -1 divided by r, and here we have the limits, and as we put in the limits we arrive at this result. Now so this result is valid for all possible curves L. And in order to arrive at this statement that we have a conservative electric field, we need to assess a closed line integral. So that gives us this situation. If we imagine that we have a closed contour L here, so this is our contour L, then we start at this point, we go around the contour, and we end at the same point. Obviously then, the distance to the origin, this that we called r sub a for the starting point, will be the same as r sub b. So these two are equal. And since this curve starts and ends at the same point, r sub a is equal to r sub b, then obviously this parenthesis evaluates to 0, and this entire line integral becomes 0. So this closed line integral now, that circle means that it's a closed line integral, will always evaluate to 0, no matter what curve we have. This applies to one point charge. Obviously, this result would apply to a superposition of point charges as well. And if it applies to a superposition of point charges, it applies to any charge distribution, should it be a volume charge density, a surface charge density, or a line charge density. So we can have any complicated electrostatic charge distribution. This result holds anyway. The electric field produced by that charge distribution, as long as it's static in space, will have a 0 closed line integral. So this closed line integral always evaluates to 0, no matter what closed contour we pick. We can pick this one or that one, doesn't matter. All possible line contours, this result applies. So that makes the electric field in the electrostatic situation conservative.